test test
Oh,
okay a little bit delay
okay, I understand.
Test.
okay test
Something delay. Okay, no problem.
everything good
Okay. Oh. Can I begin? Oh, okay. Just two more, little bit to waiting. Okay.
Introduce you first พี่อ้อเริ่มเลยใช่ป่ะไม่รอใช่ไหม Okay, maybe we can start now. Okay, good afternoon, everyone. I think all of you know me already. Okay, so today we are here to talk, to listen to a very special talk from Professor Yoshio Okamoto from Osaka University, Japan. And the topic today is about why it's so difficult to forecast the earthquake. And are GR laws in earthquakes and complex systems. Maybe the topics in the process not the same. So GR law in the GR law in the big earthquakes. So we will see that. This topic is absolutely fantastic for us. Our speaker, Professor Yoshio Okamoto from Osaka University, will introduce and give more information about this topic. He is a professor and expert in geoscience education and programming in various computer languages and more. So we can see the detail later. So please welcome Professor Okamoto, please. Okay, Professor, please.
สวัสดีครับこんにちは It's the first time to lecture to this university, a very, very good university for the surrounding the forest and very, very comfortable environment. So I enjoy my lecture and stay this universities. My English is not so fluent. My English is like Japanese English. So maybe if you can't understand, please raise your hand. Because just I excited some things, very, very fast talking. At that cases, raise your hand, stop. more slowly you are talking like this, no problem. And also, lecture is sometimes very, very boring things. So today I prepare for you a little bit, you are interested or I'm not sure, such very funny games for simulation games for the earthquake behavior. So just enjoy my lectures. Okay, at first, who am I? My career is like this. Main career is a high school student. No. High school teacher. Not many years for the student. It's very strange. So, okay. And after that, I teach in university for 10 years. And after that, this year, I was already retired. So every day is for me holiday. So you mean if you don't understand or something you want to ask me, don't hesitate. Please to email me. Email address is like this one. Yoshio Okamoto @gmail.com. All email are welcome. So don't hesitate. Please to email me. And I have one English website, just like this. But if you use Google, Yoshio Okamoto or Yoshi Okamoto, maybe you can find my website in Google. Now, you can try something, no problem. Okay, so this is my English website. At first, my website shows the Japanese side, but something is a pointer or something, no pointer, or bar or something. Sorry. Okay. Okay.
So you can slide from here, from this one.
Okay. Sorry.
Place this one too. For the next page.
Yes. Pointer. Pointer. This one. Okay. You can the title, image, and this one to change the language. Japanese or English is just here. So click these pages. And I already to develop some educational tools for high school students. Yes.
This one, no need to place that.
This is suitable for me. So sorry. And yes, this one. Okay.
Test again. Yes.
Okay. You see this seismicity map. Maybe this floor. Maybe this floor. Yes, behind this room you can find this three-dimensional earthquake maps. But maybe most of you are physics major student, I heard. Why this? Just you can see some glasses. Through the glasses, this image looks three-dimensional. So for your homework, why this glass looks generate the three-dimensional images? This is optics, physics question for you. I don't say some answer here. You think, why this glass three-dimensional? Or this is for the high school students, some fault experiment. Maybe tomorrow I will show you the high school student. And this one is a tsunami simulation I developed using the normal PC. It takes about a 2-hour calculation of the tsunami generating to takes 2 days. Because this tsunami is 2011. at that time, I have one PC. But this PC takes 2 days for calculating 2 hours tsunami wave processing. But maybe now, it may take 2 hours or something, very, very rapidly, the PC calculating. Also, this one is just skipped. So the next, we developed also some digital gadget. Sorry. Yes, I have here. As you know, some students, it's a very, very small microcontroller. Name is M5 stack. Very small microcontroller having a LCD display. Only 2,000 bahts from Chinese companies. 2,000 bahts. Very, very cheap one. Not cheap. But you can see one sensor here. It's atmospheric pressure sensors. Very sensitive. If I use this one and to more downward, atmospheric pressure is changed. Only 10 centimeter or 20 centimeter we can measure this barometer. It's called the microbarometer. If you're interested in, please to search my website. And left-hand side is my handmade seismograph systems. Now just a physics room. I choose transport them for the air mails, but unfortunately, at the transporting process, a little bit broken now. So I will repair in a week this one. Maybe you can check this one, your physics room soon. Okay. This is a microbarometer I already talked. Also, this is a science website of Ubon Ratchathani universities. I already talked to the university student and high school students about the earthquake science. So they already to show up my lecture for high school students like this. Also, this is a field trip to the outside the geological formations. This is very, very famous, very old art, wall art, very famous. Okay, so just now the today's contents. Maybe in Thailand there's a little earthquake, few earthquake. So maybe someone knows the name of the Richter scale. This is the size of earthquake. Do you understand? Size of earthquake, not the shaking strongness. Shaking strongness is called other terms, seismic intensity in English. Seismic intensity is just sitting here, or shaking something. It's a strong or weak. This is a seismic intensity. But this is a Richter scale. For high school student, I just talked to the, this difference is, you can see right, upper right here. And you can see the table is just brightness. This table brightness is changed close to the table or far table. Strong brightness or weak brightness. In this case, this brightness change is called seismic intensity. This is a change that place to place. But as you know, this light is not changed. This one, how bright? this maybe this one is something electric power. So 50 watt or 100 watt or something. This 100 watt or 50 watt, this is similar to the Richter scale, magnitude. You can understand? This difference is a very important. But Richter scale is he is Richter, C.F. Richter, and others. I just show you the Gutenberg. He's a different seismologist, and two of the seismologists decide to how to calculate the magnitude, Richter scale. They are calculated from the amplitude of seismograms. But sorry, this process is take a long time to explain. But such amplitude is calculate parameters. So we can use this one. This one. This one. Such the formula, amplitude and distance is to calculate from to the magnitude. It's contain a logarithm. This is very important point. I will show you the what's the difference of magnitude. This is a very, very impressive video to show the magnitude difference is how the energy difference. You can see the very small earthquake to a big earthquake. But you can see here, Kobe, Japan, 1995. This size, a little bit small size earthquake hit our town, Kobe. It's 6,400 people are killed by this earthquake. Small size, but very, very close to the city, underground. So very many people are killed. But you can see more and more big earthquake happens like this. And you can see that only the one, this number is growing, or 0.4 growing. The size is something like that. Very small changes of the earthquake magnitude number is a very big change of the energies like this. You can see the Tohoku Oki 2011. Very, very big earthquake hit our countries, and 20,000 people are died, killed by this tsunami. But you can see, I talked to the Kobe earthquake. Is just the energy sizes like this, very small ones. So if you have the Richter scale or magnitude, very small change to show a very big energy changes. Please to input your brains. Okay. So his famous two seismologists, Gutenberg and Richter, find a Gutenberg-Richter's law. What is Gutenberg-Richter's law? This is a famous for seismologist. Seismologist means an earthquake scientist. Earthquake is sometimes seismology because it's a very, very old Latin languages. Seis means something shaking. So Gutenberg-Richter's law is very, very popular for our seismologists, but maybe not popular for the normal peoples. I will show you what is this Gutenberg-Richter's law. Okay. So next is your exercise. Just an example of the Japanese earthquakes. JMA, this is a science office to observe the earthquakes every day. And they made a catalog of earthquakes. Its a period is like this. And this square means something the latitude and longitude limit of these areas. And they count the number of earthquakes during this period. And you can see your seat today. You can see the 2 of seat today. Page so sorry. 1, 2, 3, 4. Please look at the page 4. This one. This right-hand side is on the page 4, like this. You see here. And you can see here a table. Sorry, it's a Japanese caption, but you can see the table here. We use this exercise to plot these tables. Okay, so please look at this table and just to separate like this, no problem. So before the pages, page 3, you can see these pages. Plot here, left-hand side, these pages. Please plot here this magnitude and the number of earthquakes. You can see the 5.0 here, 5.0. And also 5.2 or 5.3 or something like this. And the vertical axis shows the number of earthquakes. Sorry, some point are missing the numbers. Just to write down Sonsip, Sansip, Sisip, Fosip, Hasip, Hoksip, like this. Okay, and here for room, so for sorry, Roy and Roy or something. Okay. At first I will plot here. 5.0 is just to read the number. Sorry, just read the number. 632 is just a number. So please plot like this. Like this. Understand? Red triangles. It means 500 and 600, 700. This number is maybe here. Not so precise. Like this. This is a couple of the 5.0 and these numbers. Do you understand? Yes. Very good. Do you understand? Not so difficult. For the university student, it's a very sorry, just another resource print out to them to print. No print. They have no handout. No print. Yes, don't have. She. Oh, okay. Do you understand the plotting? Maybe easy for the university students. Okay, just the next stage, 2 rounds. Second round, like this. Second round means next 5.1 and these numbers. 581. 581. Here, 581. Just 5.1 is here. Here. Okay. And the next. Please to continue this plotting. I just show only like after your exercise. I show you the tree of the point plot like this. Okay, maybe a little bit to take a time of the this plotting. Sorry, not so long time I have. So just to the summary of this plotting, you can find a linear relation of like distribution of earthquakes. Maybe some one not completed, but maybe suppose such relations. It's a very, very impressive relations. For us, this relation is happy. Why? Let's think. Why this relation is happy? Small earthquake is many numbers here, but the big earthquake has a small numbers. So we are happy. Do you understand these meanings? Do you understand? If this is a reverse, very, very bad things for the human. Okay, but such a small number, small energy earthquake is many, but a big earthquake is seldom. This relation is just plot the graph, very fine linear relations. This is a surprising result. This is a Gutenberg-Richter laws are important, very important points. Okay, and some students ask me, this vertical axis, you can see that this is a logarithm scales, like this. But why this is not a logarithm? No. This is a linear scale at a glance, but as you know, magnitude already contain logarithmic calculation. So it means that this energy, if the energy to plot here, this is also the log E. So that this scale graph is a number of logarithm, energy of logarithm, like this. So, but in this case, the plotting is a very, very good lineation shows. So, I just talk more. This relation, happy relation, for the humans, happy relation. If Richter scale magnitude increase plus 1, how much increase or decrease of numbers of earthquakes? You are a physics student, so maybe very, very precisely to thinking this decreasing. This is decreasing. And for me, an earth scientist, not a physics major, geology, earth science is a very, very science. It's something that 1/10, 10 times smaller, decreasing the M5, M6, and M7 or some things. This is happy relations. Big earthquake doesn't happen frequently. Okay, so this relation is Gutenberg relation or Gutenberg-Richter scale. As you know, this is my plot for the Excel, on Excel graph. You can see the very, very fine relation. But sorry, your data and my data is a little bit different. This is not a 600. This is more than 1,000. Why? you can see period is different. Your data is 1961 to 1999, but I use a more longer length data used. This case, the number is a little bit, just upper side shifted like this. So let's imagine more long time if you observe and make a data catalog of Japanese earthquakes. For examples, this is a 50 years. If you use 500 years data, let's imagine how to change the graph. Let's imagine how to change. This is only the 50 years data, but 10 times longer length, 500 years. What change happens? Maybe very easy we can find. Like this. Do you understand? Data is more upward increases. More upward increases. And you can find that 500 years in Japan. Maybe the more big one happens here. Do you understand? But no seismologist suppose such Richter scale 9 is just happened in Japan. No one supposed. Very strange things. All seismologists in Japan already know such things. Maybe the graduate school, their careers. Also me, I'm teaching earth science in high school. Maybe at that time, 2011. This is maybe the 30 years or something my careers. But I don't suppose such a big earthquake happened in Japan. Maybe this is a very strange thing. Just I will show you later that it's sometimes to call the cognition bias. Maybe such things don't happen. Psychological bias. Such things not happen. But nature is a very real things. Just this one happened 2011. No seismologist supports this one. Do you understand? But why we have no 500 years data? If we have a 500 years data, we immediately plot these graphs. Answer is very simple. We have no seismograph, seismic observation system in 100 years ago. Only this system built 50 years or 70 years after. So we have no such longer data. So no one doesn't suppose this big one causes. Okay, so next is this relation is everywhere around the world or every time statistics. You can find, sorry, it's a Japanese, so that this means Western Japan. Western Japan is a little bit smaller numbers. This is Eastern Japan, very earthquake active regions. But Western Japan and Eastern Japan, similar lineations. Also, you see the Java, Indonesia, California, or Caribbean Sea. Caribbean Sea means North America and South America. The central is Caribbean Sea. You see a very similar relation you can find. It's a very strange thing. Every time, everywhere, this relation exists. Why? But one very interesting thing is not Java. Java is not the linear here. Java is something like this. Why? Let's think. Any idea? Any idea? Java is not a special place. Maybe GR law are established, but now not established. Why? Any idea? Indonesia, developing country. This is a hint. They have no seismic network, dense network. So maybe they cannot catch the small earthquake. Maybe more 30 years or 50 years in the future, their earthquake detecting technique more good. Maybe this one is something like that. It's only the observational bias. So this is only just a downward like this. Okay. Some questions? Okay. But a very, very beautiful relation you can see. But the second problem is, maybe you are a physics student. Why such relation happens? Why? This is a very, very maybe important question. But sorry, in these years, still there is no reliable theory or equation to explain why this relation is caused. If you find that this or why some things are new theories, maybe you can get in the future Nobel Prize in physics. It's a very, very important because if you find such the equation or theories, you save very many people from the earthquake happens. Because this relation, why this relation? This is solved. It means how to cause the earthquakes. You just to explain how to cause the earthquake. Earthquake mechanisms fully understand, fully explained. But sorry, not now. It's still not found. But some very interesting models are already developed this 50 years. I will show you one theory. He is a Japanese physicist, Otsuka. So this is called the Otsuka model, or here, Go game model. Sorry, I don't know the Go game rule, but it's something like I will show you the playing the Go game or some things. And this Go game model to explain why GR law is caused. Very, very easy to understandable models. I will show you, but boring lecture, not boring lecture. Let's play games for these Otsuka models. Next one. Just I use very, very old my presentation slide. So sorry, the 2003 at Canada, I just to present this slide. Sorry. I'll just skip. This background is such ones complex systems. In 1990s to 2000, at that time, one academic movement is very, very important for the researchers. This is called the complex system. This is a physics-based something, the thinking theories. And the key word is a fractal, self-organized criticality, or chaos. Such word is a very, very many papers are published in this period. And they use the cellular automata or Monte Carlo simulations. This is a PC-based, very easy to build the simulations or game-like such models are developed. It's very famous one is a game of life. Please to use a ChatGPT or some things. You can find what is a game of life or a void or some things. And this to the similar simulation is today I will show you the Go game models. Very simple rules. So play these games for me, with me. Just I will show you the rules, very simple rules. Do you understand? Not lecture, play games now. Okay. So let's prepare this one. The grid printed paper. Please to look at these papers. I will show you how to play. You can see the grid here. Okay. And to have one pen. Color pen is maybe good. But no problem for a black pen. Color pen is maybe good. And just close your eyes and just one point to touch like this. And if you touch here to write a star mark here. Star mark here. Do you know? Star mark. Like this. Okay. Oh, maybe a different mark, okay, no problem. But I like star mark. It's a beginning of earthquakes. Let's imagine. It's a beginning of earthquakes. Okay. Just one point, please to choose. Just one point, please to choose. Okay. But what is this? I will explain a three-dimensional. Three-dimensional I will explain. This is something like underground. It's a rock, and the rock is just to contact here. Rock and very huge rock is contact here. And very, very strong pressure come here. So in this case, very, very strong pressure. Some places are rock. Very big pressure. Down. Breaks. It means sometimes a window glass breaking or something. It's just a similar thing happened here. Do you understand? So, now one point is broken. But this breaking is to propagate the next rock. Maybe. Such the breaking is sometimes to contact to the next block. So mathematically, very to use the simple rules. Not every direction. Only 4 directions we can imagine. For example, 1, 2, 3, 4 directions. This breaking is to more next side or not. This breaking is something the next block also breaking or not breaking. But this suppose image is very difficult. So we use, pencils. This is just predict the future. Such is a very good pencils. Okay, and you can find this pencil already get to the 2 green spot like this. And you just like this. This rounded point is very bad. So only the hexagonal point is like this. And if you look at the green point, this is a lucky point. The breaking is to propagate the next grid. It means, but no green surface appeared. This breaking is not to propagate the next stages. Do you understand? And this numbering is no problem. Reverse or 1 is here or something, no problem. You can easily choose a 4.2 only just numbering. So at the first dice trial, this is a dice. First dice trial for number 1. Please do trial like this. Okay, just trials. Lucky or unlucky, just trials. Only once. Okay, just show a lucky student. Just show a lucky student. Oh, very few. Maybe the probability of the 1/6 probability. No. 2 of surface means a 1/3 probability. Show a lucky. Okay. If you show a lucky, in this case, just write a circle. This is a lucky. But sorry, if not lucky, in this case, just write a X. Write a X. Like this. Please here to write down. Okay. Just to translate to Thai or someone. Okay. Sorry. Please to explain in Thai. Okay. Only once. And if the lucky circle, not a lucky X. Yes. I will show you. Okay. This is the first round. Second round. Number two is the second round. Please do more. Please like this. Also, the third stage and the fourth stage, please repeat the dice. Okay, finish the 4 times. Finish 4 times. Someone don't have lucky. All are unlucky. Please raise your hand. Just this is sometimes God throw a dice like this. So you are a very good God for humans. Because the earthquake is ended very small one. It means only no lucky. It means only one position is broken. In this case, please to listen to me. In this case, if all 4 points is unlucky. In this case, the cluster size 1, only cluster 1 size is broken. So you see this one. As you know that to count a number like this. Sorry. You can use a counting number like this. So, how many numbers cluster 1 is caused? So, in this case, all unlucky students just see 1 is 1, like this. And to the next stage, just to closing eye and some point to choose to repeat this process. But sorry, just next, if you can see something lucky one here. In this case, I will show you how to make these trials. Please look at this one. In this case, this one has 4 neighboring point next trials. In this case, 1, 2, 3. This one. But this one is already marked. So not to write here. Only this one and this one and this one. Also, this one has a 4 point. So in this case, already this one is a 3. So next is a 4. And next is a 5. And here, no chance. So in this case, you have 5 times trials, dice trials. Do you understand? Okay, let's begin a second trial like this. And if you only one cluster ended, please to repeat the next point, starting point, writing star. This process is repeat. Okay, let's trials. Let's playing this game. Okay, just to stop the game, and I will show you the cluster size, how to count the cluster size. If this trial is ended like this, all are surrounded, all trial are surrounded, unlucky like this. This case, this earthquake has 1, 2, 3 grid size. Rounded 2 and the original 1. 1, 2, 3. So we write down the 3. Cluster is 3. It's just once, like this. And next trial, like this. Next trial, to like this. To many earthquakes, you can try in this games. Yes.
The first one, if I have two circles.
Yes. And in this, no. In this case, more trials, because this one is a 1, 2, just trial.
So I need more trial until,
Okay.
until
Yes, until surrounding. It means 1, 2, here 3, 4, 5 times the next trial. Yes. No, nothing. Just surrounding the unluckies, just ended. Yes.
I found the green point.
Green point. It's yes.
Okay, so this one is big. It means that you
Break. Yes.
But for this one, it just
Not break. Yes. Yes. maybe in high school sometimes I just teach my simulation game for my class. But the next class, social science or national language or something, get angry because a student more and more times to play this game for the next class or something. But sorry, it take a long time. And my university classes, just to gather your data, how many earthquakes happen in a whole class. But sorry, today I have no time to gather your data. But maybe you can imagine small earthquake many times happens. But a big earthquake is a little bit small probabilities, not so many times happens. So we can gather this data at the classrooms. Sorry. This one is a rule, and if you remember, it's a figure 2 is a rules of Go game model. Please show this game rules. And this is my result. Sometimes such the result is cause big earthquake or small earthquake or some things. And you can see the this graph. This graph is earthquake number, and the horizontal axis is a cluster number. How many clusters are breaking? Cluster numbers. If you use this graph to your all data to come together and to plot here, you can expect this result. It means only one cluster or two cluster earthquake many times happens. But the big cluster size earthquake is not so many times happens. You can see something similar relations, just the ZR law. Do you understand? If we consider this cluster number, it takes logarithms of the cluster numbers. It's the same as I just show this one. This one is the same because this is earthquake size logarithmic. And this is earthquake numbers. So this simulation shows a very similar result of the earthquake size and earthquake numbers. This is the first published to explain why in the nature such earthquake size and number relation is beautiful line like this. Do you understand? And also, this game rule is easily to change the PC simulations. So, I developed such style of the PC games. This is, you can see the red color is the first origin of earthquakes you choose. And white means lucky. But blue means unlucky. So we can change this game for the very easily to compute simulations. So this algorithm to apply more large areas like this. Red color is the first origin point, and white color is a lucky number, lucky point, like this. Small earthquake, many earthquake, and sometimes big earthquake happens like this. But in the computer simulations, we can adjust, change the probability of the breaking to next one to transport something. So if you use more big probabilities, this one is a probability is 0.58, more than half probabilities. Such very strange kind of earthquake will cause. This is a big earthquakes we can suppose. So in this case, computer simulation continues. Such no earthquake spaces, many such the small earthquake happened in that places. So at last, this relation of the size and number of earthquakes looks like very good relations. This is my calculations 20 years ago. Very good calculation. Lineations like this. This is a natural earthquake, but this is a simulation earthquakes. So this model explains why GR law is happened. So some seismologists believe this model is maybe true, maybe explain a real earthquake happened. But next is a very important thing. Please to think, if the earthquake prediction program has two tactics. Sorry, I just skipped. Now the two tactics is a little bit failed, maybe failed as seismologists think. So this model suggests the size of an earthquake strongly depends on a stochastic process. Stochastic process. Do you understand? This is not a stochastic process. Maybe in the ground, underground, some friction change or rock hardness or rock weakness, maybe to decide this behavior. But this is maybe a very mathematically difficult to modeling. So we use a stochastic process for this modeling. So in this case, this is a very important things. Please write a line here. This model is, if true, the earthquake prediction is not, can't predict the earthquakes. This is something that, in principle, this is not. Because I just show you, the size of earthquake cannot be predicted before the event occurs, or an earthquake does not know when she ends. You understand? Only knows the God to throw the dice is only know. But we cannot know this rock break is just ended or more continued. Of course, this is physical. Maybe we can know. Because every rock strongest, we can observe. If observe or friction constant, observe many points, every point of the underground we can know. Maybe we can estimate, calculate such the prediction. But this is a realistic no. Because we can't digging a hole or we can't measure the force or some things. So this model suggests that an earthquake not a simple process but a complicated one. So if it is true, both small earthquake and a huge one have the same starting process. And the size of earthquake is completely controlled by a dice. God controls the earthquake size. And in this case, the model destroys the optimistic view of an earthquake predictions. Okay. Just 1975, such a very interesting model already published. But unfortunately, his published paper is written in Japanese, not in English. So no one knows this his work more than 20 years or something. And in the 1990s, his work is discovered. And maybe he is a pioneer of such I just show you the cell automaton model. Cell automaton model. So you can see this one. I just show you the very, very similar one here. This one is a computer simulation. But this one is a very simple. Just two files and pouring the water inside. Sorry, not water. This is oil. Oil inside. Just like this. This is called the percolation models. Because oil is penetrates like this, and very, very similar models. In the physics field, please to check the percolation model or some things. You can find these models. Also, just to talk the 5 to take a rest, but 5 minutes. Another percolation or cell automaton, very, very simple go game. Now, here, set a fire, but this field is covered the forest green and vacant ground blue. In this case, some probability fire to next tree to burn up or something to use probabilities. So in this case, some big probabilities. The forest is something like that. The fire is very extending like this. But the probability is small. Or forest is not dense inside. In this case, the forest is stop the small fire. Do you understand? But this model is also applied. Let's think. This forest fire model apply another models. Let's think. What's a model? Apply these algorithms. These 3 years, we are very, very get more and more disaster by this disaster. What things? These 3 years. COVID-19. Do you understand? This is a humans. Green is a humans. Red is just COVID-19. he is sick, she is sick. In this case, some probability to propagate other humans like this. Do you understand? So, already such the physicist or medical scientist to make such disease epidemic models. Very similar algorithms. Very similar algorithms. Do you understand? You can see such the Gauguin model-like simulations like this. Also, my same algorithm Gauguin models. And you can see the black point is but white is and green means the sickness of the COVID peoples. And cured, red shows just to become a health, some things. So you can see that this is a very resemble your earthquake clusters. Do you understand? Earthquake and the COVID-19 cluster is maybe same behaviors. For me, it's a very interesting thing. Do you understand? But some different fields unites maybe the one algorithms. For me, it's a very, very interesting point. But for you, I'm not sure. And this, my simulation shows a very, very similar behavior of the pandemic propagating simulations. So this Gauguin model also uses such the pandemic simulations. It means that maybe the earthquake and the pandemic, COVID-19 pandemic, maybe has a very, very similar mechanisms. I just suppose. But COVID-19 has a vaccine, but earthquake has no vaccine. Do you understand? Okay, just take a break for the 5 minutes. Okay, just take a break. Okay. There are many other models to explain a GR law. I will show you. This is other models. One model is sand pile models. The left-hand side person is a Parback, Belgian. He's a Belgian. He published a very famous paper, sand pile model. Maybe you can get the knowledge from the ChatGPT. Okay, so this model uses a very simple calculation process. Only 3 process, very easy to programming. But for the high school student, maybe this calculation is a little bit difficult. So I made my original sand pile model like this. What is this? Okay, I will show you. Okay, just so this one. What is this? You can see the vacant here. This means 0. And one circle, this means 1. Three triple circle here. This means 3. This means 2. Like this. All sand pile is limited 4. If get 4, this sand pile is broken. And just the 4 pillar is broken. 1, 1, 1, 1, like this. Do you understand? I just to show you. Please close your eyes. Just one point like this to select. Choose. In this case, this one. This one is just one circle added like this. Or anyone here. Here, this one. Just to add the one circle here. And next, like this. This is a vacant, so one circle hit like this. But if you choose a 3 triple circle like this, in this case, this get a 4. But 4 is not prohibited. In this case, this one is collapsed. And collapsed 4 is distributed. Here 1. Here 1. But sorry, here is already 3. This is collapsed. And this collapsion, just 1 here, 1 here, and 1 here, like this. It means this collapsed place is 1 and 2 are collapsed. This is same as Go game model. This rock is broken. This rock is broken. Like this. Do you understand? But sorry, today I have no time to play this game. So, in this very simple rules, we use computer games like this. This is a real high school student play these games. But they said, oh, just my eye is rounding like this. Very, very, just a bad problem. But as you know, Thai university students don't play mahjong game. Not Minecraft. From China, mahjong game. Mahjong game uses such not a card or something that like this or like this or like this. This is very, very similar to the mahjong games. So I call this for the mahjong game or something, but not popular. And you can see the computer simulation also makes such clusters. This is a computer games, computer simulation I developed. And a very big cluster happens like this. This is the same of the Go game model. And in this case, the broken, as you know, the broken grid cluster and the number of the it's an earthquake model. So it's an earthquake number and the broken size is a very, very beautiful linear relation shows. Do you understand? But in this case, we don't know the underground condition, where the rock is something very, very weak or where the very strong or something. I don't know. So in this model, also the very, very difficult to the earthquake predictions also shows. Okay, this is a real sand pile model, but I have no time to talk this one. Also, the next one is such models. This is something block and spring, like this. And to move this one is something one directions. So you can see the friction is a block and floor. Friction applies. In this case, something happens. I will show you. Here, this is my student. Just experiment. It's a iron block to connect the rubber band. So he to pulling this rubber band. Sorry. We are going to this one. Okay. In this case, some block is just to slip because a rubber band to pull the blocks. But he count which block is slipped, or sometimes 2 or 3 block same time slip or some things. It means only one block slip. This we think that small earthquake happened, but many blocks at the same time just slip. This means a big earthquake happens. So such it's a kind of simulations. We can find as you know the same relations. Block number and the frequency like this. This also shows a very similar relations. This is a one-dimensional model, but also some other person think that two-dimensional models. And the equation is like this. And of course, I made this model with my student. This is maybe for me, it's a first and only. No one tries such things. But we play these block models. And to sleep or not sleep or same, how many numbers or like this to count. This is a real experiment. I just show you the videos. You see sometimes sleeps.
1個
Sometimes sleeps. Oh, just like this. It's the same time or only one or something.
2回動いてから14になります。
waiting for sleeping.
2個
More slowly too. Okay, sorry. not much. And in this case, also the same block number and the population frequency is a little bit like this. So, this model is a more interesting thing is this one-dimensional model shows sometimes one of this block is just sleep. In this case, the next earthquake very mostly happens the next one. This one sleep. In this case, this one or this one maybe sleep. Just predictable. So, my student just shows that this is a time interval, and this two block sleeps, and the next time this block sleeps, or something like that. Such a time sleep shows that something sleep is too shifted like this. And very interesting thing is, this is a Turkey earthquake. Turkey earthquake, Anatolian fault is here. But this place is a very interesting thing is, just here sleep, the next is, this is old one. Here sleeps are very old. But some year after, the next one is here. And after, this one is sleep. And this one is sleep. And this one is sleep. Just sleep the area of the propagation to some fault system. So sometimes might be to predict the place. But this is only the where next cause a big earthquake. But when is very difficult. Only the location or place we can predict. Sorry, just to skip. And next one is GR law. Frequency and size distribution. And I already talked to you, this is a logarithmic scale. Logarithmic scale. In this relation, it's not limited on earthquake or forest fire or COVID-19. This relation is many places we can find. I will show you some examples. This logarithmic and logarithmic is make a linear relation is called the power laws. Power laws. And most, just skip the, this one. My student makes studies. What is this studies? I will show you. this is a map of Japanese, one island. So she uses a compass, mathematical compass. And what things she is now doing, please look at carefully. She uses a compass to measure the length of the island seashore's length. 1, 2, 3, or something. So it's a compass radius multiple number of sorry. Not this one. Here, he used a compass to repeatedly like this, and measure this length. But if you change the compass width, more smaller one, narrow one like this, the length changes. How to change? Let's examine. Let's imagine. To measure such the length of the seashore's length to using compass. If the compass is more smaller wide, this is just like this. In this case, a more small land and sea surface the shape is we can find. So in this case, a more smaller measuring, the total length of the seashore length is longer and longer and longer. So they made such graphs. If the compass width is more shorter, the seaside length is more longer. This is the same relation we can find. So next one is a more another examples. You can see many craters on the Martian surface, but small crater is very many, but the big crater a little bit few. In this relation, this is a crater size, diameter. This is a number of craters. You can see a very similar relation you can find, like this. Big size crater is a very small amount, but the smaller crater is a many amount. Also, this one is another examples. This is the size of volcanic eruptions. Big volcanic eruption is here. Small volcanic eruption is here. It means small volcanic eruption many times occur, but a big eruption not many times occur. This is a very beautiful linear relations. Understand? We found such a relation many times, and also not the natural systems, but something the social system we can find. Let's think about what is this chart. Let's imagine what is this chart. This chart means one thing. Let's guess. What means? Let's guess. This images. this size means the frequency of the some you read the English newspaper or some things, and many words appeared, but such word frequency, because this is very very frequently using word. Understand? Oh, very very good student. So this is a word, and this is just the ranking of the frequencies. Ranking. Top one is a Z. Next ranking is of. Next is and. Like this. Sorry, this is not the size. Not the size. In this case, this is a ranking. Ranking of word. Frequency rankings. Do you understand? In this case, more frequent to very, very small frequent, you can see. But very strong, strange thing is just lie on linear lines. Very, very strange. This is called, this relation is called, sorry, you can Google to use Zipf's law. Zipf's law about word frequencies. Very, very interesting relations. Zipf's law. But I will show you another Zipf's laws. For me, I try such things myself, try to myself. But for me, very busy. So my student, just come here. And you can read this newspaper. Please to count the word frequency like this. And my high school student made such the frequency ranking made. And this is not our student. This is a network. But my student just making these data. Economy word, economy, some newspaper, economical, some news, they count this number of frequencies and make graphs. Sports from the newspapers, same. Anime, like this. This is a very, very similar relation my student find. Okay. And the next one is this one. Such the relation is a word ranking, word frequency ranking. Next is this one. Do you know this magazine? Very famous magazine for economists. Fortune is a journal name. And they, every year, they are just to the data of the company ranking, whole world company ranking, or how get the money or some things. Just company ranking they made. This company ranking is like this. This one, Fortune Global. Global means a whole world company rankings. Top one is Walmart in US. Second one is State Oil. Maybe this one is an oil company. And third is Amazon, the US bookstore. And also something like this. And just a change of the years. But Walmart is something top, like this. This also shows a ranking, company ranking, and gain or get the money or something. It's very, very linear relations. This is very interesting. Left-hand side is, I just skip this one. Sorry. This is a Japanese food chain ranking. Very similar. But as you know, the two graphs. This one is a logarithm and a logarithm. But this one is a normal axis. In this case, you can see this one is turned to the logarithm and the logarithm, the linear relations. Sorry. This is a very bad rankings. This is a death rate of the war. It's a World War II. Very, very many people are died. World War I and French Revolution, Vietnam War, or some things. This is some death rate of the war rankings like this. But as you see, this war and others are very, very not the same lines. It means these two world war is a different kind of wars we can find. Such the characteristics of war we can find. And the next one maybe, sorry, in Japanese, maybe it's famous for Thailand. Some TV shows, maybe you can see this one. This is election ranking of AKB48. AKB48 election ranking. Very, 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 very beautiful delineations. But not every year. This year 2016 is a very, very beautiful lines. So I like this chart. So this is another year of ranking. Not so delineation is beautiful. Okay, but one more examples I will show you. This is a goal ranking of football. Goal ranking of football. Blue is 2012 to 2013. It's world goal rankings. World goal rankings. Lionel Messi, Cristiano Ronaldo, Falcao, or like this. It's very, very beautiful linear relations. But at the same time, this is a Japanese J-League goal rankings. This is a world. This is a Japanese J-League goal rankings. The difference you can find. This is maybe the Japanese people just a chance of goal, but just to present the player like this. So the Japanese people is something very kind for the other player. So not to make the straight line. This is my opinion. Sorry. Okay, I just show. And also, okay, something such as a power law. It means a very, very huge amount of book sales or something sales, or in YouTube you can find many times looking the YouTube movies. But on the other side, only 2 or 3 times only to watching the YouTube movie or something you can find. But YouTube contains a very, very huge amount of popular movie and very, very small amount of seldom watching YouTube or some things. So this person is a very, very interesting report. He writes Wired. This is some things are net journals. He's just sees in Thailand, Amazon is not so popular. Amazon is only a cafe or some things. But in my company, Amazon is not the book sales. Many things, everything to sell to the network shoppings. In this case, Amazon is many items they sold. It means Amazon usually the convenience store or some things, only 20% of the items get 80% monies. Only 20% very frequently sold items get much monies. But he said Amazon is not. Because Amazon sold a big stockyard. Only one book, 1 year, just sold. Such like very small size business can realize to the network business systems. So they thought Amazon is not the 20% book sales, the 80% of money, get money. He said Amazon's very frequently to treat the get money is only a 0.5% or something, he said. More half is very small sales, but many items they have in the stockyard. So in this is called the long tail, he said. This part of the getting money is very big. Because this is realized by a network, internet systems. So he says a new such the merchant system, such a business system, we are now finding. This is his story. Please to check the long tail. Long tail. He's published. Also, the one is a black swan. Maybe someone knows the black swan. This story is normally no black swan. No, there's nothing such a black swan. Normally thinking, but some 30 or 50 years ago, I don't know. In Australia, they discovered the black swan. Species black swan. It means no one supposes, not causing such things or some things. This is an example of the Tohoku earthquakes. We can't suppose such things don't happen, but it happens. So the Nassim Taleb is his name. He published such very not supposed thing is maybe some probabilities they cause such things. Power laws for natural disasters. If the time span becomes longer, more big disaster is expected. I just to talk to you at the first. If the data gathers 500 years, 2011 Tohoku earthquake can expect it. More long time, more big earthquake will happen or some things. So this is to depend on data spans. Also, this possibility is somewhat large, not supposed, but sometimes occurs. People do not believe the event is larger than their experience. It means, in my lifetime is 60 years or 80 years or some things. But some natural disaster causes more than 100 years or some things. In this case, the people don't understand such event causes. So the Nassim Taleb called the black swans. But such things is something our kind of cognitive bias. Not this such event happens like this to thinking. Okay. Only two slides remains. The last one. Predictability of such things. Let's imagine. You are physics major students. Planets or rockets are maybe the 99%, not 99%, maybe completely controlled by Newton's mechanical law, Newton's law. Maybe controls this planet's location or moving speed or rocket of some things. But weather forecast is not 100%. Nowadays, weather forecast probability is maybe it's depend on the countries. In my countries, 65 to 75% or some things. This means tomorrow will rainy or some things. And if the rain comes, it's just true, but not rain. In this case, forecast failed. Such probability is maybe weather forecast is 60% to 80% or some things. Stock market. This is very, very difficult. Very difficult. If I found an equation for stock market, I just stop my lecture now and I build a stock market forecasting companies. Do you understand? Get much monies. But maybe no one knows tomorrow's stock market, which company is high or which company is low. This is very difficult, maybe 50% or some things. These are predictability of stock market. And more difficult thing is human brains. His thinking or her thinking. Do you predict? Can you predict? Maybe this is a very, very difficult. For my experience, maybe 30% or more low or some things. And human history. Do you suppose 1 year after the Ukraine war is ended or not? Very, very difficult to predict. Human history is very, very difficult to predict. And my question is, do you think earthquake prediction is this ranking? Do you think? My opinion is maybe here. Earthquake prediction is very, very difficult. This is my opinion, like this. So, the final slide is just even your future you can predict? Maybe no. Very difficult to forecast like an earthquake to forecast your future. So our lives are filled with surprising events. Okay, not forecasted. So your life is good thing. not predict. So your life is a good thing. Do you understand? And thank you very much for watching. Thank you very much. Just today's PowerPoint file will be uploaded, but sorry, I cannot to upload my contents to my web server because maybe the web server company prohibits foreign countries' FTP transfer. So I will come back to my country mid-September, maybe the 20th or something. So after that, I will to upload this content. Also, please to visit my website. Okay, thank you very much.
Okay, any question from the audience? No. มีคำถามไหมคะ ไม่มีเลยเหรอ อาจารย์สมเจตถามเปล่า Oh, okay. So may I ask one question? So you did the simulation for finding out the earthquake, and do you have the experiments? I mean the result from the seismograph or something like that to compare to the simulation?
Okay. Sorry, her question is computer simulation. I will show you, but she asked me. I have lots of seismographs. So, such using the simulation or using the seismograph record, do you predict the next one earthquake? Sorry, not, because my simulation, tsunami simulation, this is a very, very easy to make because the tsunami wave completely obeys a physics equation, wave equation. This is a very, very simple equations. Maybe a little bit linear equations. So such the wave propagation is maybe not completely, but 90% we can predict to more future. But the earthquake is not a wave. This is a something broken event. Such broken event is physically called a non-linear equation or non-linear behavior phenomena. In that case, prediction is very, very difficult. Sorry, this is my answer. Yes, please. Very good questions. The volcano is caused by a magma moving. In this case, we can detect the magma movings because magma moving, very many earthquake happens the surrounding areas. So we can monitor such places many earthquakes happen in recent years or something. So we can suppose maybe the magma is moving or something. So active volcanic eruption can predict sometimes, But natural earthquake, not related to magma or something. This is a very, very difficult. Nothing to find the way of the, because this is only the underground force causes such natural earthquakes. In this case, it's very difficult to predict the next week earthquake. Magma-related earthquake can easily to, but sorry, only the not earthquake. In this case, magma eruption may be predicting. So magma and earthquake is a different things. Thank you. Very good questions. Any other questions? Yes. Hi.
So it is possible to use a machine learning or AI to make an equation to put inside and then predict the earthquake.
Very good questions. To predict to using AI or machine learning system. Now some earthquake scientists using this method, but never succeed. Sorry, never succeed in this point. But in the future, some possibility, but not big possibility, I think. Only 20% or something just has AI. Because AI is something similar to our brains. So something, the revolutionary idea coming, maybe it's possible. But now we have the item or we have the tools, maybe very impossible. Okay.
นักศึกษามีคำถามอย่างอื่นอีกไหมคะ You can ask in Thai and in English โอเคถ้าไม่มี I would like to thank all of students and the staff that come here and see the interesting seminar from Professor Okamoto. And thank you for your talk today. And Professor Okamoto will be around here in this week. If you have any question or you have any idea to discuss with him, please feel free to join and talk to him. You can find him around at the office of Science Project at the building 2. Or maybe at the Faculty of Physics, Department of Physics. He will try to set up the seismograph at the Department of Physics. Okay, and finally, I would like to invite Assistant Professor Dr. Gontip to give the souvenir from Department of Physics and from Faculty of Science. ปรบมือ